Okay, well, again, it's wonderful to be here. Thanks to the organizers for inviting me. I'd like to start just by saying a few general words about the subject before getting into a couple of specific new topics that have come up in the connection. Something that an enormous amount of exciting effort has gone into over the last 2 decades is making more and more sense of and understanding more and more deeply the left picture here. Best instantiated in the gauge gravity duality, where some kind of quantum mechanical system is king, is fundamental, and out of it emerges space and gravity and strings and all the rest of it. Well, for around 10 years or so, I've been pursuing something that's kind of a step beyond this. Of course, it's more speculative. It's not obvious there's actually anything there. But it's more an idea like this. So there's some other structure, not where quantum mechanics is primary and space is emergent. You see, in this picture, time comes along for the ride. And we have all kinds of deep cosmological reasons, amongst other things, to believe that time should not come along for the ride. It should also be emergent somehow. And if time is emergent, it's very hard to imagine the sense in which quantum mechanics could be fundamental too. So space-time is going to be emergent. It seems sort of inevitable. There has to be a third structure out of which quantum mechanics and space-time emerge together, somehow joined inexorably. And if this is a different talk, I can give you lots of circumstantial evidence or reasons to believe that something like this might be true, in addition to the more concrete things along these lines that we've been finding over the past 10 years or so. But since it's a string math conference, let me actually give a more technical, directly related to the internal logic of string theory argument for looking for something like this, which is simply a huge, to me at least, a big tension between the two big lessons of the mid-90s. In the second string evolution, on the one hand, there was a picture of the world where there was one massively unified underlying theory, and all the different corners were seen to be solutions, different backgrounds of the same underlying thing. On the other hand, we have the gauge gravity duality that has, from many points of view, the opposite feeling about unification. That any old quantum mechanical system is dual to its own private theory of quantum gravity and the bulk. How can both these things be true at the same time? Well, it seems very reasonable, something that many people have said, a very vague statement, that I think is an exciting vague statement, that it could be that there's a kind of a counterpart to this picture that we should be looking for, a kind of a more universal, unified bulk description of the physics, which would probably have to give something up. That something is probably won't be as manifestly normally quantum mechanical as we're used to talking about. If you demand precise quantum mechanical observables, you have to go out to the boundary, and then you're stuck with this. So if there is some kind of more universal, unified bulk description, it's not unreasonable or crazy to think that it would have to be more relaxed about being manifestly quantum mechanical. That, to me, motivates studying the aspect of bulk physics which is more universal, which is the flat-space part of the physics. Part of the fact that the real world is not too far from flat space, which is a good motivation all by itself. But even purely formally, the hope is that we can study and understand more deeply the flat-space estimate in a way that does not hardwire in not just the inside of the space-time the scattering process is taking place, but also any kind of a picture of quantum mechanical Hilbert space. That might give us the right clues or the hint of the right kind of mathematical structures we should be running into to somehow get back into the bulk. So this is a very vague hope, but I think something needs to be done, at least as far as I'm concerned, about the big tension between these two pictures. All right. So more concretely, this is the question that many of my friends and I have been spending 10 years or so thinking about. Imagine you're an experimentalist at infinity. You throw particles in, they come back out. You have no idea what happened on the inside of the space-time to give rise to the histogram cross-sections and everything else that you've measured. It's the theorist who tell you that what happened to give rise to the complicated patterns of collisions that you saw was local unitary evolution in space-time. But from the point of view of this measurement, the space-time is in your head. It's a way of giving a story for what actually happened. And so we're interested in finding a different story, some other set of rules that could give rise to exactly the same physical observables. And of course, this sounds a lot like S-matrix theories, but the philosophy is kind of opposite to that of the S-matrix theorists of the 1960s. The S-matrix theorists, here's the main problem. The main problem is that it's not at all obvious it's obvious how to check the S-matrix as Lorentz invariant and unitary. It's not at all obvious how to check that the S-matrix is consistent with causal evolution in the interior of space-time. That's supposed to be reflected somehow in the analytic properties of the S-matrix, but no one knows a priori what those analytic properties are. And the people in the 60s imagined they could derive this slavishly somehow from general principles, and that program failed. So what can we do better now? And apart from having watched more theoretical data and working with more promising theories and more technical things, I think we have a different strategy, which is not that we're going to slavishly derive these rules, but that we're going to guess something. We're going to look for some new principles, some new structures, out of which causality and unitarity will be outputs, will be derived things, rather than being the primary things that we're putting at the beginning. So let me be even more concrete. So you're talking about scattering amplitudes, and what are they functions of? One way or another, you can say geometrically is that this is physics that lives on the boundaries of Minkowski space. So how do we think about the boundary of Minkowski space? Well, from the point of view of concretely of this question, it's just any old way of talking about the physical on-shell. Let's say we're talking about massless particles, massless null momenta of the particles. You can use just good old-fashioned momentum. You can use twistor variables. You can imagine labeling things by the energies the particles have and the direction they go out into the celestial sphere. There's all kinds of different variables that you can choose that are one way or another variables for the boundary of Minkowski space. And if we're talking about cosmology, then we're talking about something even simpler. We're just talking about the flat spatial slices in the deep future. So that's the tangent. But in this space, we have to somehow find a question whose answer has all of the richness and complexity of scattering amplitudes or the wave function of the universe in cosmology. And it's not obvious what that question should be, because unlike the boundary of anti-consider space, there's no useful notion of time and no obvious notion of locality here. So this is now a question. What kind of questions do you ask directly on the space where the functions you're interested in are defined that sort of breathe physics-like into the space? It seems pretty boring and arid, just a space of null momenta. But that's the question we've been pursuing for 10 years. And the picture that's emerging is that this aspect is actually very recent. Just in the last year, we can finally say these things directly in the boundary of Minkowski space, if you like, directly in the space of on-shell particle momenta. But that in this space, there is essentially combinatorial structure that's associated with what we're calling positive geometric structures, and ultimately, further, the geometries are associated with certain canonical differential forms, and those differential forms are the things that are directly related to physical observables like scattering amplitudes and the wave function of the universe. So I'm not going to go through this picture in any detail, but just to put a tiny bit more flesh on the bones of the words I said, in this d-dimensional kinematic space, just the space of null momenta, or any of these other ways that you might want to label them, there are certain good regions, we call them positive regions, that are in one way or another associated with interesting positivity conditions. But this can be a sort of a large capital D-dimensional kinematical space. Physical observables like amplitudes or the wave function of the universe are associated with lower dimensional differential forms that live in this high-dimensional space. And there's also an interesting family of subspaces that intersect with this positive region in particular geometric shapes. So these positive geometries are compact regions that have boundaries of all possible codimensions, codimension 1, codimension 2, all the way down to codimension 0. Polygons and polytopes are the most trivial familiar examples, but they generalize beyond that. I'll say a little bit more about that in a moment. And so on these subspaces, the intersection of these subspaces of this positive region reveals these geometries. And these differential forms that encode the information about the physics are slaves to this geometry. They have the property that they have to be a certain canonical form associated with this geometry when they're pulled back to that subspace. All right, so let me just say a little bit about positive geometries. The most simple examples are just, for example, the inside of a triangle or the inside of a polygon, just geometrically. We can think about these insides as just, if we think about everything projectively, that the points inside the triangle, or inside the cone projectively generated by the vertices of the triangle, are a positive linear combination of these external data, these z's. So here's the first notion of positivity, that being inside the triangle or the polygon is associated with these numbers, these coefficients being positive. Now, on top of that, the external data has to have some positivity as well, for the shape to be nice, for the shape to be a convex polygon. The determinants, these brackets in this talk, are always going to be determinants. The determinants made out of any set of 3 consecutive ones of these z's, any 3 ordered z's, sorry, not necessarily consecutive, all have to be positive. So there's a positive linear combination of some positive external data, and so that defines the inside of the triangle, the inside of the polygon. And on top of that, there are canonical differential forms that have the property that they have logarithmic singularities. They're locally coordinates that look like dx over x, dy over y, etc. On and only on all the boundaries of this positive geometry. As I said, for polytopes, this is relatively well known and not trivial, but interesting. What we've been seeing over the past several years is that they generalize beyond polytopes to many other spaces in interesting ways. So this was the first example that we ran into around 4 or 5 years ago. The object we called the amplitude. I won't talk about the extension to loop level, which is much more interesting. But already just at tree level, there's a geometric object that calculates scattering amplitudes and maximum supersymmetric gauge theories. And it's just a generalization of the previous picture into the Grassmannian. So previously we had these points y that were points in projective space, we just generalize them into the Grassmannian, but it's exactly the same formula that we have k of these points that gives me a k-plane in some k plus m dimensions, and there are positive linear combinations of positive external data. But now the notion of positivity here involves a matrix, and instead of saying that the entries are positive, you have to say that all the ordered minors associated with this matrix are positive. And once again, the external data also has a notion of positivity associated with it. So this is a generalization of polytopes into the Grassmannian. Actually, some of my math friends told me recently that Gelfand was going around in the 90s telling people, you polytope people do trivial things all the time. What you should do is figure out how to generalize polytopes into the Grassmannian. So here we are, 20 years later, doing what he told us to do. Okay. Now, a final thing to say about this is one of the new things that arose just in the past year or so. That picture that I gave you is, well, you know, even for ordinary polygons and polytopes, I've given you the convex hull type picture for the interior of the space as a positive linear combination of the external points. But there's another way of talking about this space as being bounded by its facets. The sort of inequalities definition of what the space is. And it's natural to ask whether the second definition also extends to these more, fancier situations with Grassmannian. The answer is it does, but it does so in a kind of, in a subtle and interesting way. It generalizes it. So here we have some configuration of points. They're positive in the sense that I told you. And we're interested in this, some k-plane in k plus m dimensions. And this is good. It's in a good location relative to these guys. In the previous picture, it can be expressed as a positive linear combination of the external data. But how can you decide if that's true? And the answer is to decide that it's true, you have to project this whole picture through that plane down to a lower dimensional one. And in the lower dimensional one, the new configuration of points that you have has to have certain topological properties. It has to have a certain maximal winding number. or even if you project all the way down to one dimension, it's completely determined by certain Seinfeld patterns. But there's something basically topological about what this configuration looks like after you project through this space that determines it. And I won't go through this in any detail, but other than say this is really the complete description of what this space is. So it fits on this slide. In this example, the physics of locality and unitarity, physics of space-time and quantum mechanics in this example arise really joined at the hip from this quite primitive combinatorics in geometry. And now this combinatorics in geometry is seen in kinematic space at infinity, in the place, in the space where the amplitudes are supposed to live. Okay, so that's, and of course, this stuff actually describes the real world. It describes the real world in some approximation, but every time cosmic rays hit the upper reaches of the atmosphere with energies, so the center of mass energy of the collision between the protons is significantly bigger than a GeV, the underlying gluon collisions at leading order are described by this mathematical structure. I find that quite fascinating. Okay, once this picture became apparent that we could look for these geometries at infinity, that opened the door to start seeing them all over the place. So now we've gone well beyond maximally supersymmetric theories. Back in the fall, there's a wide range of theories that are in a somewhat different way, but still in kinematic space associated with ordinary polytopes, interesting generalizations of Stachel polytope, generalized associahedra, and so on. And also in cosmology for the wave function of the universe. Again, in perturbation theory and a broad range of theories, there is an interesting new class of polytopes that has a similar relationship to them as these objects have to scatter amplitudes. So there have been many new developments of this subject just in the past 6 months, and if you're interested in them at all, they'll be discussed in talks at the Amplitudes Conference, which is going on simultaneously with this one later this week. So some of those talks will be online, and if you're interested, you can take a look. But I want to switch gears and now talk about something else which has emerged in the past 6 months, which is beginning to see the same, very, very similar positive geometric structures in completely different places. So these are the two topics I want to spend the rest of the talk telling you about. We've been seeing these positive geometric structures in effective field theory, so you could call the resulting spaces F-dehedrons. It sounds like a dirty word, but this is associated with a hidden positive geometry of causality and unitarity, and it puts lots of constraints on the structure of higher dimension operators in any effective field theory. And once you see that story, you will immediately think about the conformal bootstrap in conformal field theory, and indeed, there's essentially exactly the same geometric structure that's associated with the conformal bootstrap. And so those are the two things that I want to tell you about for the rest of the talk. All right, so let's begin with the F-dehedron. This is work in progress with Yuting Wang and Chuchu Huang. So this is a certain universal geometry that controls effective field theory, and in particular, we're going to see infinitely many quantitative predictions about quantum gravity in the real world. So we'll have constraints on photon-photon scattering, graviton-photon scattering, actual things where those photons and gravitons are our photons and gravitons. All right, now, let me remind many of you, most of you know this very simple story. It's actually an ancient story that goes back really a long way, but was popularized again by a number of us 10 or 12 years ago. You might think that we don't really know anything about the structure of higher dimension operators in effective field theory, unless we know everything about the ultraviolet physics. So low-energy physics is dominated by the marginal interactions, dimensionless interactions, and there are some higher dimension operators that tell you something about the high-energy physics, but unless you know what the ultraviolet theory is, you don't know what they are. In fact, already over a decade ago, it was pointed out that we know a tiny bit. We know, for example, if we have a theory of photons, and we look at the first, after the fourth corrections, then we can show on very general grounds that the coefficient of these operators has to be positive. And that positivity has many forms. If the coefficient is negative, then if you turn on translation, you get a varying background like a constant electric field, then perturbations around that background can propagate superluminally. So that's bad. So you want the coefficients to have the right sign not to let that happen. And you can also derive them, and this is what we'll be generalizing in a moment, you can derive them from basic conditions having to do with causality and unitarity of the estimate. So, at least for myself, this was the first interaction with a kind of trivial notion of positivity. And then there are all these fancier things that have come along later. And what we're going to see now is they're actually very closely related to each other. And the fancier things are really greatly generalized this early stuff. I should also add, though, that this positivity is crucial for protecting the consistency of horizon thermodynamics. For obvious reasons, the superluminality is very bad for the notion of horizon. And it's related in interesting ways to weak gravity conjecture. For instance, if you just turn on the entire dimension operators, if they have the wrong sign, they will make the mass-charge ratio for extreme black holes go up. Whereas the weak gravity conjecture leads you to believe that the mass-charge ratio for extreme black holes should always go down when perturbed by the fact of the higher dimension operator. All right. So let's talk about the objects that we're going to study. I'm interested in the 2-to-2 scattering amplitudes, where it's the two identical particles, A and B coming in and A and B going out. And I'm going to say a little bit of fine print, but whatever velocities the particles have, there's a low energy piece of the scattering amplitude which just looks like contact interactions, and those are what we normally associate with higher dimension optics. So we can expand the contact piece after pulling out a piece that depends on all the velocities as just a sum of some powers of the nanoscience and T variables. And so these are the guys that I care about in this talk, these coefficients. So I can separate these guys into a piece that carries the overall units with the dimensions that capital B reflects the overall mass dimension of this of the corresponding amplitude, and these guys that are the kind of ratios of the ratios of the different guys with the same mass dimension are dimensionless. In fact, they're naturally projected. So this is the data of the problem, if you like. Really, it's these A's, but just for the purposes of this talk, I'm splitting them into the pieces that carry the dimensions and the dimensionless pieces. And this is what we're going to say about them. These guys are going to satisfy infinitely many nonlinear inequalities. This is putting in the intuition that you can't have dimension 6 operators suppressed by a TE with the dimension 8 operator suppressed by a million TE. They should all roughly be suppressed by the same scale. Okay? So we'd like to make that intuitive notion precise, and that's going to make that, so that'll be done there. And these guys, these dimensionless things that just live in projector spaces, not only they have certain positivity properties, which we already knew before, but much more than that. They're not just positive, they have to lie in very specific polygens. Okay? Very, very specific polygens. In fact, these are all special cases of a single, more abstract, unified statement, which is very much like that y equals c dot z statement about the amplitude, but I probably don't have time to talk about that here. All right, so let's talk about where this comes from. Just causality and unitarity, in a very familiar way, tells us that we can expand amplitudes at fixed small values of t in the following way. So there are some pieces that we'll talk about here. There are subtraction terms that have to do with the rate of high energy growth of amplitudes at small fixed t and large s. This really causality tells you that at fixed t and large s, the amplitude has to be bounded by the power of s squared. So with that fact, just Cauchy tells you that they have these pieces that we can't say anything about, but then everything else has to be expandable in terms of things that only have poles in S. This sum, I'm writing as a sum, it could be an integral, so these could be poles or branch cuts, it doesn't make any difference. And furthermore, that the residue on one of these poles can have some dependence on T, which if you sit on this pole is a dependence on the scattering angle. And the dependence on the angle must be such that you could imagine expanding this, and experimentalists seeing this resonance would say that they produce a particle with spin s if they can expand this guy in terms of Legendre and general spatial dimension Gegenbauer polynomials of the cosine of the angle with positive coefficients. So the positivity here is the probability of producing the particle, So unitarity tells you that these numbers are positive. So this residue is a positive expansion in terms of Gegenbauer polynomials. And of course, we don't want to have any tachyons up there, so we assume the mass squareds are positive. So this is the question. We would like to know what is the consequence of the Taylor expansion. What's the consequence on the expansion of this guy in SMT of this underlying positivity for the mass squared in these probabilities? All right, so let's go. Before doing that, let me just do a lightning review of polytopes 101 because we're going to be doing this over and over again. This is completely trivial stuff. Kids in grade 7 are maybe better at thinking about it than grown-ups. But if you think about, just think about again the inside of a polygon, you want to imagine all the points on the inside of the polygon are weighted sum of the vertices. And as I already said before, with positive weights. As I said before, it's better done projectively, so I can think of the cone instead, and so now I'm looking at all the weighted sum of these vectors with positive coefficients. And again, we'd like to know, if you hand me some A, is it inside or not? And for that question, this description is not very useful. The better is the face description, where you say what all the faces of all this guy are. Kind of trivial in this case of the polygon. So when you really understand a polytope, it means that you know all of its facet structure. You know its vertices all the way up to its faces. And of course, there's a systematic way of figuring out what all the faces are in general. But asymptotically, as the number of vertices, the dimension, everything becomes large, this becomes harder and harder. Let me just say, though, that the facet structure is completely captured by just giving the signs or zeros of all these minors, all these determinants made up out of these vectors. This is sometimes called the oriented matrix of the vector. All right, now, of course, mathematicians have studied infinite classes of polytopes, many classes of polytopes for many years, but there's a very special class of polytopes that are maximal and extremal in many ways. These are the so-called single polytopes. And they're associated with a case where the vertices naturally come with some ordering, which certainly refers to polygons, but now it's generalized to higher dimensions. The vertices come with naturally some ordering, and in that ordering, all these determinants are positive. Okay? So if I say in the language of this matrix, we would say this matrix is totally positive, or it's in the positive Rachmanian, in the sense that I said before. If I think about the convex hull of all these vertices, that is also has a name. It's called the cyclic poly. And this is also corresponds to the trivial polytopic case of the amplitudes. So it's also the case of one amplitude. But what's important is not all these words, but that we know all the facets of this guy ahead of time. So that's essential. We understand everything about this polytope. So I can check whether some point is in there or not. And these are the facets of this interesting structure that looks like vi plus 1, vj plus 1, and so on. So it's pairs of consecutive vectors generalizing what we're used to for polygons, where it's just I plus 1 for the edges. Okay? So that's it's not hard to show, but it's a non-trivial and cool fact. And in fact, we know all the facet structures everywhere in between, but we'll only need these big faces for now. Okay. So let's move on then. With that introduction, let's go back to thinking about our field theory question. So the surprise here is that there are two hidden total positivities in this story. There's one hidden total positivity in just the structure of a positive of a positive residue divided by a propagator. Okay? So there's some hidden positive structure just in that simple thing. And separately, there's a hidden positivity in the structure of these Gegenbauer polynomials. Both of them generalizing the obvious positivities that people have known about for years. All right. So, in other words, this is all about locality. The poles here are about locality. Unitarity is about that positivity, and of course, also tells us about the expansion in terms of Gegenbauer. So there's some hidden positivity in locality and unitarity. So let's first talk about the positivity in the propagator. So let's take a simple example. We can take t to 0. So we just have a simple sum that looks like this, and of course I can trivially Taylor extend. And so these coefficients, there's a trivial formula for the coefficients, just doing the expansion of that guy. So there's the question. If you give me all these coefficients, A0, A1, A2, how do I know they can be expressed in the form that comes from this formula, which is sum of Pn over Mn squared, and you just Taylor expand these out, 1 over m squared, 1 over m squared, 1 over m to the fourth, and so on. So the most obvious thing is that they're all positive, because these numbers are positive and the m squareds are positive. But of course there's much, much more, because this is just saying that these coefficients are inside the convex hull of a bunch of points. I don't know what they are, but a bunch of points that lie on the moment curve, 1, x, x squared, and so on. Now the moment curve is the most classic example of a curve where you take a bunch of points on the curve, you have a cyclic polytope. That's because all the order lines are really positive, the determinant is van der Waals, all the order lines are positive. So these guys are inside the convex hull of some cyclic polytope, but I don't know ahead of time where the vertices are. So it's a smooth version of the cyclic polytope. And now here's a little exercise to figure out what cuts this space out with inequalities, and it has an interesting answer. So this is not entirely trivial. But the interesting answer is that from this vector of coefficients, A0, A1, A2, and so on, you make the following matrix. You just write all the coefficients down, shift it by 1 as you go, down to lower and lower rows. So the ij element of this matrix is just little a, I plus j. It's called the Hankel matrix. And the claim is that these guys are the convex hull of the moment curve if and only if all the minors of this Hankel matrix are positive. So that's a very interesting link between total positivity and unitarity. Okay. So here's the most trivial example, is when you have when you just have A0, A1, A2, which are in the convex hull of 1xx squared, that just looks like a parabola. Okay, so the x's are positive, and we have to use the convex hull of any set of points on this red curve, so that's just by I, that's obviously the inside of this parabola. So in order for these guys to be in that region, I have to have both that A1 is positive, and that A2, A0 minus A1 squared is positive. And you can plainly see that that's equivalent to the statement that all the minors of this little 2x2 Hankel matrix are positive. Okay? But this generalizes more non-trivially for all the cases. So that's interesting. There is a link between total positivity and unitarity. All right. So, and indeed, so this already tells you that I can't have dimension 6 operators and dimension 10 operators very big in size than dimension 8 operators. That's that nonlinear link between higher dimension operators with different mass dimensions that I was alluding to before. All right, let's move on to the hidden positivity of the Gegenbauers. So the Gegenbauer polynomials are just gluing together two 3-point vertices, and it's trivial and standard textbook material that when cos theta goes to 1, in the forward limit, this is just a square of something, and so it's positive. Okay, so everyone knows that. That goes into the proofs of statements about the optical theorem, all sorts of other things. But it's then natural to ask what happens if we expand around 1, and let me collect all the Taylor coefficients together of the Gegenbauer polynomials expanded around 1. So let's look at what they look like. So this is what it looks like in the particular case of Legendre polynomials for spin 0, 1, 2, 3, 4, and these are the Taylor coefficients y to the 0, y to the 1, y squared, y cubed, and so on. So the first statement that the Gegenbauers are positive in the forward limit is just that the top row is positive, and they've been normalized to 1. So that's obvious, and everyone knows that. Slightly less obvious, but still pretty trivial, noticed by many, many people, going back at least to André Martin in the 1960s, and I'm sure by mathematicians long, long before that, is that all of these Taylor coefficients are positive. Okay? And that's something that doesn't immediately follow in some obvious way from some positivity of a norm and Hilbert space argument. Maybe it can be found in that way. I haven't tried too hard, because it's totally trivial to derive this from just a generating function for the Gegenbauer polynomials. But the new statement is that all of the minors are positive. And the old statements were just a one-by-one version of this bigger one. Okay? This Gegenbauer matrix is totally positive in the sense of the positive Riemann. Okay? Now, in the particular case where the Gegenbauers are cosines of Chebyshev polynomials, this fact was actually known as Chebyshev in the 1850s. And actually very interesting how Chebyshev was kind of a pioneer in thinking about total positivity for reasons having to do with interpolation theory. But the generalization of the statement to general Gegenbauer polynomials, as far as I know, is new. All right, so that said, in particular, if I take the top k rows of this matrix, it's a in the positive Rashmanian. If I take the convex hull of the top K rows within the cyclic polytope, and so on. Let me actually tell you what the deeper statement is from which that one follows. The deeper statement is actually not about any Taylor expansion about a particular point, but just taking any collection of spins, S1 through Sn, ordered, and any collection of points, x, but not in the physical regime for x between -1 and 1, but in the Lorentzian regime for x, where they're ordered, again, and bigger than 1. Positivity, remember, means an order. So here the ordering is provided by ordering the spins and ordering these points in the Lorentzian region, where cos theta is replaced by cos eta. And the claim is that all these minors, all these matrices made out of evaluating the Gegenbauers for ordered spins and ordered points are positive. That's the deeper statement. When you take these guys and shove them all on top of that point, you can derive the statement about the Taylor expansion that I told you a moment ago. Anyway, so now, both those facts are now going back to my slide, are going to tell us, the first fact tells us that all of these coefficients out in front, the overall strength of the coefficients, the dimensionful part of the amplitude, these satisfy those Henkel matrix nonlinear inequalities. And these guys have to lie within specific polygons. In the most sort of trivial version of this, the toy version of this problem, where all we have in the expansion are poles in the S channel and not the U channel, then the literally cyclic polytope doesn't have time to explain the expansion more generally, where the projection of the cyclic polytope and the polytopes are slightly more interesting, but this is the essential images that are going on. All right, so let me just then show you what these bounds actually look like. And I've already described what the nonlinear bounds and overall coefficients look like. So this is what it tells you about these dimensionless ratios that you have if you live in particular regions. So for instance, here I'm talking about photon scattering. This is the expansion. You can't see it. The z variable corresponds to S minus u. So this is an SU symmetric scattering amplitude. And the lowest order piece, there are two coefficients for z squared and t squared. The space is one-dimensional, and the bound is that one. Okay? So there's a specific number, -7/20, and that comes out of the Legendre polynomial. That's a fact of Legendre's life. Okay? When you go to the next set, there are three operators, so two ratios that lives in a two-dimensional projective space. And they're being plotted with the axes are chosen cleverly as a linear combination, as the geometrically motivated linear combination of these operators. But anyway, once you do that, this is what the polytope looks like. You see, it has infinitely many spins, infinitely many vertices. They pile up as you go to infinity. And so there's spin 4, spin 3. You see, it's interestingly inverted. This has something to do with what I told you, that this is one of the cases where you actually get a projection. So it's a slightly, the vertices are ordered differently than you would naively have expected. But anyway, it's all predictable. And so you might have thought, what's wrong with having, one of these guys 7 times bigger than the other? You just can't do it. No amount of tuning, nothing you can do it. These are sharp numerical, quantitative predictions about photon scattering in the real world. There are three-dimensional versions of this. These polytopes don't look very pretty because they're pretty skinny, which is actually interesting. That means that they don't vary very much, which is separately not obvious ahead of time. That actually has very little feeling about why that ends up being true. And anyway, similarly, we can make statements about graviton scattering, the analog of the one-dimensional constraints have a -1136 here, and the polygon here looks very similar. It's not identical, and in fact, it's a very different linear combination of the coefficients that are involved in making it look this way. So anyway, just to give you a flavor. So my takeaway from this is that, and of course, all of these things are just a big extension of the old statement from over a decade ago that some of the higher dimension operators are positive. So my takeaway from this is I've always believed that the world is not a crack of metals, that it's not just governed by some kind of garden variety technical theory. There's much more constraints coming from Lorentzian variance, something that we have in the vacuum of the real world that we don't have in garden variety finesse matter systems. And in any case, there are vastly greater constraints on the one effective field theory than naively expected. And there are many questions that are still open. Can we extend to full nonlinear constraints of UV completeness, really ultraviolet unitary? which says that not just that those probabilities are positive, but they have to be small enough to be compatible with unitarity. And can we actually use this kind of argument to really prove rigorously that in any theory that's causal and unitary in the ultraviolet, shifts in the mass-to-charge ratio of extreme black holes go down, and that would go a long way to putting the weak gravity conjecture on more solid footing. All right, now, how long do I have left? 5 minutes? Okay. All right, so this part will have to go a little faster. So now we're going to talk about exactly the same things in the context of CFTs. Okay? So this is going to be the geometry that's associated with conformal bootstrap, and we'll get exact constraints on CFT data that follows from positive geometry and very simple combinatorics. All right, so I'll just quickly remind you that this beautiful program that Polyakov laid out in the 70s is to imagine just completely determining conformal field theory determining CFT 4-point functions just by doing an OPE expansion in 2 different channels and equating them. So the OPE and unitarity, the OPE and unitarity tells us that we can expand a 4-point function as a sum over conformal blocks with positive coefficients. So again, this now turns it into a positive geometry problem, into a simple geometry problem. We don't know what the geometry is yet. And crossing, and there's also the restriction of crossing. So the Polyakov dream was that solving this problem is like classifying Lie algebras, and the difficulty is that there's infinitely many operators and it's much more complicated. So the big question that many, many people have done a huge amount of beautiful work on over the years, analytically, numerically, all sorts of ways, is what does the allowed space of allowed deltas, spins, and these coefficients, what does it look like? So we know, presumably not everything is allowed, we know many things are not allowed, but what does the space actually look like? That's really what we're interested in. Now, for simplicity in this talk, I'm going to consider only SL2R blocks and work also on the line z equals z bar, just to make things as similar to the previous story as possible. So now we just have the function of z that's expanded as sum over delta, there's no spin, of some positive coefficients times conformal blocks. And these conformal blocks are very simply z to the delta times this famous hypergeometric function. So, if you want to, this is an infinite problem. It depends on the continuous variable z. You could make finite versions of it. For example, you can sample at n different values of z and write down the same formula. That gives you a big vector that's now written as a sum with positive coefficients of a set of vectors that you care about. I could talk about Taylor expansion coefficients around some point z star, ditto. So the obvious question is, now that we've talked about one of these finite problems, what is the shape of the polytopes that are made of the convex hull of these block vectors? I mean, that's the first thing that we're doing. Unitarity tells us that these vectors are in the convex hull of those ones. And, of course, this is now what you go looking for, given what we've seen elsewhere. And the statement is that they're totally positive. Okay? So this is a non-trivial statement, that if you take these hypergeometric functions, you evaluate them from Z1 through Zn up to Z1 through Zn for dimensions now. Now the order is in dimensions, before it was in spins, now it's in dimensions. That this is a totally positive matrix. Now, I should have mentioned, in the case of the Gegenbauers, we have a proof of this because it's pretty simple to just compute the determinants. Okay? We don't have a particularly conceptual proof, except in the case of cosine, where we found Chebyshev conceptual proof. Okay? So, but beyond that, even for Gegenbauers, we don't yet have a beautiful conceptual proof. And that is hurting us here because we don't actually have a proof of this statement. Okay? But we have extensive numerical evidence that it's true. It's true. We can take it to the bank. Okay? All right. So given that that's true, now unitarity is a statement that the 4-point function, or any approximation thereof, is in the convex polytope made out of the blocks. And now what is crossing symmetry? Crossing symmetry is a simpler statement that it's relating the value of the 4-point function at one z to another z, so it's enforcing the 4-point function lives on a half-dimensional plane in the big space. Okay? And so this is the geometry problem that we're invited to solve that for the bootstrap. We have a certain cyclic polytope made out of the blocks, and we have a crossing plane. And what the crossing plane is depends on the dimension of the external detail, if these guys live in a 2n plus 1 dimensional space, this crossing plane is basically half-dimensional. It's n-dimensional. And so there's two geometric questions. Question one, what constraints do these deltas have to satisfy in order for this crossing plane to intersect the polytope? So that's equivalent to what are exact constraints on the spectrum that at least in this dimension, make it possible for this plane to intersect that polytope. And question two, once you know that it does, what does the intersecting polytope on X look like? Okay? And that then tells you exact constraints on the 4-point function. Okay? And those are the two questions we'd like to tackle. Before going further, I just want to give you a sort of a similarity. They're very, very similar problems. The setups are very similar, but with different emphases between studying the tree amplitude and the CFT. In both cases, we have some plane, lower dimensional plane, in a big space, which is spanned by positive external data. For the amplitude, the positive data is fixed, and we're interested in some property of this plane. It moves around, and we're not only does it need to intersect this polytope, but it has to do so with this corrected winding that I mentioned before, this correct binary code. The difference with the CFT hedron is now the crossing plane is fixed. It's the same picture. The plane is fixed, but we don't know ahead of time what these deltas are. And so as we move around between different CFTs, the actual detailed shape of this cyclic polytope changes, and it may or may not intersect X. So we're interested in figuring out the constraint on, first of all, the constraint on the deltas that allows, as you move them around, that allows them to intersect, and secondly, what the intersecting shape looks like. But we don't need it to do it in any particular topologically correct way. This guy merely needs to intersect that way. Okay? But the problems have a similar character. Okay, I think I don't have any time to talk about this in detail. Let me just say that, but just to get a very rough idea of the character of constraints, already in the simplest case where this crossing plane is one-dimensional, and this is a picture that everyone who studied the bootstraps in any direction is familiar with. It's just seeing it from this point of view. If we just take that picture, that's a three-dimensional picture with a line intersecting the boundaries, the two-dimensional boundaries of a cyclic polytope. If we project it all, the whole picture through the identity block, we get a simpler-looking picture of just a curve that looks an awful lot like a parabola, with the dimension 0 down here, going up to dimension infinity up there, and then we have this crossing plane, which is just a line, and you see that it intersects with some delta minus and some delta plus. And those delta minus and delta plus are very important, because if I now imagine populating specific deltas, this is a specific candidate spectrum, this one's good, because the convex hull of all these points certainly is intersected by that. But any one where there are no operators between delta minus and delta plus are bad, because they can't possibly intersect. And so we learned something already in this trivial case, that there actually must exist some operator. It's not the lightest operator necessarily, but what we know is that there must exist some operator that's between delta minus and delta plus. And furthermore, if you look at the smallest one in that range and the biggest one in that range, then these guys, these walls of the underlying cyclic polytope, intersect the line and tell me where the 4-point function is bounded. So that's a really trivial example in one dimension. Already going to 2 dimensions, it looks a lot more interesting. Now the crossing plane is 2-dimensional. Now we would first like to see what is the constraint on the delta data in order for the crossing to be able to take place at all. And one very easy way of doing that is to just project the whole picture through the identity as well as the crossing plane itself. And you get these interesting looking curves. And even the shape of these curves depends on what the value of the dimension of the external operators is. But the requirement that the crossing plane intersects the upstairs cyclic polytope is simply that if you now put a discrete spectrum on here, it admits a triangle that encloses the order. And again, that puts interesting constraints on the spectrum. So if I draw this picture, and I knew there had to be someone between delta minus and delta plus, now you learn more. Depending on where that guy is, there must either be, the next one must be in this range. If the first guy, the highest guy in this range is beneath this interesting tangent line, and if it's above that tangent line, then either the next operator must be in this range, or if it isn't, there must be some lighter operators that are in this range. Okay, and this is a kind of global constraint on the spectrum of CFTs that you can get in this way. So if these are satisfied at x intersects, there are various applications of this simple picture. For example, we can bound the lightest two operators. Famously, they're bound on the gap of the spectrum, but we can also get interesting bounds on the spectrum of the lightest two operators that follow in a trivial way from that picture. But much more interestingly, there's also, on the crossing plane, there's a particular polygon that you end up getting there when it intersects the cyclic polytope. The shape of that polygon, which is the constraint on the 4-point function, depends now in detail on the spectrum, and it does so in an interesting way. For example, here's a putative spectrum of the CFT, and all you have to do, since you know the underlying walls look like I plus 1, jj plus 1, the vertices have to look like some triplet I plus 1, j that's borrowed from a wall on one side or the other. So there's a little combinatorial problem about how you put all these guys together. And you can solve, for any given spectrum, you can solve this combinatorial problem. So if we have a spectrum that looks like that, the 4-point function is bounded inside this polygon. But if you move this point, 3, and you move it down to the other side of this blue line, the shape changes. It changes to a pentagon. If you move this point 6 and move it to the other side of this line, it changes in a more interesting way, to an infinigon. Now it starts getting infinitely many vertices that go out in that direction. And these things all happen in interesting CFTs. So this is the infinigon for a free fermion, for different values of delta phi. This is an infinigon for some funny CFT with a weird spectrum, but it's not infinite. This one now just looks like a triangle. And I also invite you to look to see how narrow these ranges are. Presumably this has been seen in many other contexts, but I find it kind of amazing that these are exact statements about derivatives of the 4-point function, that they're nailed at such very narrow ranges by these requirements. But you see, these are sort of non-trivial numbers that show up here, and they show up from solving this combinatorial problem. So let me just end by saying that I think there's a remarkably rich and geometric and combinatorial structure that's associated with carving out this delta space, together with the associated polytopes that found the 4-point function. Now, I showed you the explicit solutions of this problem for the 2-dimensional geometries. We've just solved it with 3-dimensional geometries, so this is pretty easy to do at low dimension. But of course, what we're hoping for is that, as has happened over and over again in business, there's a recursive procedure that allows you to solve the problem systematically to arbitrarily high dimensions. And that's something that we're starting to focus on. Thank you for your attention.
Thank you very much.